Inconsistent and dependent systems. We saw in our graphing example what these look like in a graphing context, but what we still need to see is if we're using these symbolic methods like substitution and elimination, how do we recognize these special cases? So let's try both of these systems of equations. I'm going to try the first one using substitution, and I'm choosing this method largely because the first equation is already solved for x, so that makes it really easy to just plug that expression in for x in the other equation. And because I'm choosing substitution here, I'll choose elimination on the second one so that we can see that the way we interpret our results really is pretty much the same regardless of which of these two methods we choose to use. So if we're using the substitution method on the first one, it's solved for x, so I'm going to take this expression 2y and plug it in for the x variable in the other equation, and that gives me 2 times x, which is 2y, plus 3 equals 4y. This 2 times 2y becomes 4y. And so as soon as I try to get all the y terms onto the same side of the equation by subtracting 4y, doesn't really matter whether I'm trying to get them onto the left or trying to get them onto the right. Either way, I would subtract 4y, and all of my variables drop out, and I'm left with this equation here, 3 equals 0. This is a contradiction, just like we saw with the linear equations. And if we come to a contradiction, then just like that told us that there was no solution with single linear equations in one variable, this also corresponds to the no solution case when we're in two variables, which is inconsistent. So this is an inconsistent solution, system of equations, and it has no solution. Going on to the next one, we're going to use the elimination method here. And so that means that I need to pick a variable to try to drop out, but first I want to rearrange the terms. And I want to rearrange these terms so that the x's are lined up, the y's are lined up, the equal signs are lined up, right? It doesn't really make sense to add these together and get anywhere if the terms are all in different places. So mostly it means that this 4x term in the second equation needs to be kicked over to the left, and that makes it a minus 4x. So if I write these again, that's negative 2x plus y equals 2, and then negative 4x plus 2y equals 4. I can now choose a variable to target, and if I choose the y variable, for example, then I can make the y variable drop out by multiplying that top equation by negative 2, so that I get positive 4x minus 2y equals negative 4, and the second equation stays the same at negative 4x plus 2y equals 4. When I add these equations together, even though I was only trying to make the y variable drop out, the x variable dropped out and the number terms dropped out, so that I'm left with the equation 0 equals 0. This is what we would call an identity if we were in the context of one variable, and it had solution set all real numbers in the context of one variable. Here it doesn't, because if we remember back to that picture, it's a line that has an infinite number of solutions, but it's not true that every ordered pair is on that line. So this is the dependent system, which has an infinite number of solutions, but it's not true that it's every ordered pair. We can still express this solution set, and we should do so, using set builder notation. What we do is we say it's the set of all ordered pairs x, y such that, and after our such that, all we have to do is copy down either of the original equations, because that describes the relationship between x and y. Since both of these equations are the same, it doesn't really matter which one you take. I would take the simpler one. It looks like the second one, everything is multiplied through by 2, so I'm going to choose to use the first one, but it's still correct even if you pick the other one. So our solution set is the set of all ordered pairs x, y that lie on this line, or such that this equation is satisfied, right? So all of these could be part of our answer. Whether we're asked to say that it's dependent and that it has an infinite number of solutions, or we're asked for the solution set, we can still express our answer in one of these ways.